I welcome you all to today's special seminar. It's being given by Adil right here. Why don't you join the frame? Right here. Okay. So Adil is a research associate working with us over here at LUMS. And he, in his spare time, likes to compute generalized parton distributions, right? So he's working in the general area of high energy physics. Adil, welcome. Please continue with this special topic that you've arranged for us to.
Okay, sure. Thank you everyone for coming. So I was initially worried if there might be more people. So is it safe to assume that everybody here is familiar with index notation, summation convention, and everything? All good or no? If there's one person, I'll work for them. So don't be worried.
Open ratio.
Okay, perfect. Okay, I've made arrangements for that. So the second thing is a bit of a disclaimer, which is that this is not original work, right? So these are not my ideas. This work was done by some people in South Korea. They published a paper about what we'll see. I found the paper interesting, and I thought, I should share this stuff. But the presentation is original. Okay. So bear that in mind.
And when exactly was this work published?
This was around 2020, right, when they came up with this. And just get in touch with me. I can share the references with you. Right. Okay, so basic stuff. First of all, in this, the idea is that we want to be manipulating vectors, three vectors more specifically. So vectors that have three components, x, y, and z, or 1, 2, and 3 components. And usually, you come across vectors sometime late in high school or beginning undergrad in your electromagnetism courses or classical mechanics and stuff. And that's usually fine. But sometimes when you have complicated identities and stuff, they can start to get a bit messy, especially if you're starting out. To deal with that, people came up with a clever way of manipulating vectors, which is called tensor notation. Okay. But tensor notation has its own learning curve associated with it. So this is supposed to be like a bridge between manipulating vectors, how you're typically used to just writing them out in component form, manipulating them, and the more, let's say, efficient tensor notation. The idea is that we will take, this is essentially tensor notation in disguise. They've taken the symbols that appear in tensor/index notation, translated them into diagrams, and now we'll have rules for diagrams, and when we manipulate those diagrams, we will be doing vector computations, essentially. That's the idea. So pretty much for about roughly half the time, I'll be setting up the groundwork. I'll be explaining the rules, and roughly around halfway, we will start to see some interesting stuff. So bear with me for about 30 minutes or so. So the first thing that you come across are, well, scalars, simple. Scalars can be numbers or scalar functions. We don't really care at this point. The way we'll represent scalars is with just a box, and the label of the box will tell us what the scalar is, right? So simple, scalar f, that's it. That's how we will be representing scalars. Simple. Next come vectors, right? So again, we'll have a box that carries the vector label on top of it. But you see the box has a leg sticking out of it, right? That represents the index of the vector. You see, the index I've written I. This I can take on values 1, 2, and 3. So, I1 would be the x component, y component, or z component. 1, 2, 3. So the idea is that a vector carries one index, so we'll have just one leg sticking out of the box. Vector, yeah. The next symbol I am going to introduce is this symbol. It's a straight line with two indices at the ends, so I and j. Right. So this is our Kronecker delta. We will call this Kronecker delta. Don't worry about the name. I'll explain everything. Right. And so scalars and vectors pretty simple. Now this thing seems a bit weird. So I'm going to shift to the second board right now and explain a bit. So you see, what I've drawn is straight line with an index I and j, right? Can you move the camera to the second row, please? So it's pretty much the same thing, I and j. I can draw it pretty much this way. Doesn't really matter. It's like a loop of string, if you imagine, right? Or I can draw it the other way around, ji, right? And you realize that this ji is not really different from ij, right? I can just turn this thing around and get ij, right? So the first thing you have to see is that this thing will represent this with, this is delta ij, this is how it's typically represented. This is the same as delta ji. Right? Don't worry about the index, the symbol for now, but just remember that this has this property, this symbol, that ij is the same as ji, right? That's pretty much clear from the diagram. So what is this delta ij? You know, I have to apologize, I have to go through the details, but it's important. So this Kronecker delta ij is defined as this thing takes a value +1 when I equals j, and 0 when I is not equal to j. Right?
Can there exist such a Kronecker delta which is antisymmetric again?
I'm not sure, but we will see constructions that are antisymmetric that are made with Kronecker deltas. Okay. So for now, at least in a Kronecker delta with two indices that run from 1 to 3, right? This is how it is. So it's symmetric. First of all, ij is the same as ji. So what does this really mean? That if you plug I equals 1, so 1 and j equals 1, so delta 1, 1 is equals to delta 2, 2 is equals to delta 3, 3. That's just equal to 1.
Can I answer the question?
Sure.
So in n dimensions, you can have an n dimension, you can have an n index totally anti-symmetric pseudotens.
Like the limited weakness of the
Right. So this thing takes values +1 or 0, right? Depending upon whether the indices line up or not. Simple as that. So I'm just going to add this to the definition here, that delta ij is equals to delta ji is just equals to +1 when I equals 0 and 0 when I do not equals to. Simple enough, right? Okay. We have to shift again. I'm going to move again. Delta is pretty simple, straightforward, right? The next thing is this other one, this Levi-Civita symbol that I've written down, right? So really don't worry about the names. The names may sound a bit fancy or weird, right? You also note that I've drawn an arrow, a counterclockwise arrow here. So this arrow is meant to to signify what direction you're supposed to read this thing in, right? So we choose a convention, we're going to read this thing counterclockwise, right? So symbolically, this thing is represented as epsilon, right? And the indices I'll read counterclockwise are I, j, and k, right? But there's nothing really special about starting from I, right? I could just as well start from j. So this is epsilon j ki or kij. Right? So this cyclical nature of this object is encoded in this diagram in this way. Right? All these symbols are equivalent. Right? Simple enough. Now you might ask, okay, like the delta, what values does this thing take? But before we get to that, I need to tell you about one more property that this symbol obeys, which is up over there. So I'm going to bring this down over here. So again, we have this ijk, right? You can bend and twist the legs as much as you like. So here I've taken the I and I've pulled it down over here and I've taken the K and stretched out over there. That's fine because the ordering still reads, okay, I, J, K. But as soon as you snap two legs across this central vertex, the rule is you have to pick up a minus sign. Okay? So now by doing this, this thing was, I can read this as epsilon I, J, K. This is equals to, well, this is also epsilon I, J, K. But now, if I start from the top, this is K, J, I with a minus sign. Right. Point is, when you flip two indices, you pick up a minus sign. That's the rule. That's the rule I'm telling you. You have to, this is the part of the definition of the object. Now, this rule has a very interesting consequence, right? So, first rule was you read this counterclockwise. Second rule is you pick up a minus sign as soon as you flip two indices, right? This rule has a consequence. The consequence is that these indices I, J, K, right? They can take on values 1, 2, and 3, right? So suppose they take values 1, 2, 1, right? That's a perfectly valid possibility. But then I apply this rule. What I can do is I take these legs, these two, and I flip them across the vertex. What happens? I pick up a minus sign, right? But I swapped the indices, right? I picked up a minus sign. But look, I ended up with the same object. Right? So under what conditions can this be true?
Both of them are equal to 3.
Right? An object equals negative of itself. That's only true when the object in question is 0. Right? So just the consequences of those two rules tells you that if you have epsilon I, J, for any of the two indices that become equal for that matter, then this object is immediately 0. Right? So the point is that whenever you have such an object, all three indices must be different for it to have a non-zero value. Right? Because they take values 1, 2, 3. So you put 1 here, 2 here. This has to be 3 for this to be non-zero. Right? If you put 1, 2, 1, it's 0. You put 1, 2, 2, it's 0 again, because you can pick up a minus sign and it's equal to minus of itself. Okay. So now I can actually put down, first of all, A. That's 1. And now here, we have this, and the values this thing has been given. So the way we define it is this. So what have I written here? I said +1 for even permutations. I'll explain what this means. -1 for odd permutations, and 0 other parts. So what is an even permutation? So let's say you have epsilon 1, 2, 3. You can read the indices in increasing order. Right? That's an even permutation. Whenever this permutation appears, this is +1. According to our definition, you can cycle through these indices maintaining the order. Right? So you can have epsilon 2, 3, 1. That's also +1. Given by our rules. So as soon as you flip an index, you pick up a minus sign. So all this object is, again, it's +1, -1, or 0. Right? That's it. That's the basic language that we need, pretty much, to start manipulating our vectors. Right? So we have scalars, vectors, our Kronecker delta, and our Levi-Civita symbol over here. And now we can start playing around with them. So, first thing, I'm not going to talk much about scalars. Scalars are boring in that sense, right? Because it's just a box with nothing. Right? So let's start with vectors, right? We start with vector A. Right? Now I'll write the accompanying symbolic notation of what I've written AI symbol. This can take on values 1, 2, and 3, depending upon which computation. Now what I do is I take a Kronecker delta ij, and I combine it with this. Right? So what I've done is simple enough, right? Symbol and the translation. Okay. The rule is, as soon as you see two matching indices, they combine. Right? Every time you see two matching indices, you combine them. That's a rule. That's what I'm telling you. So when they combine, it turns into this. And what this combination is, what's actually happening is what we're encoding is we are technically summing over these indices. See, I was repeated. Right? I was here. Summed it over. Right? This is what's happening. So if you write out this sum explicitly, this is A1 delta 1 1 G plus A2 G plus A3. Right? This is what this sum represents. So you say, okay, what value of J do you want? 1, 2, or 3, right? Any value of J that you pick, what's going to happen? Let's say you pick 3, J equals 3. This term goes to 0 because you get delta 1, 3. I and J are not equal. This goes to 0. This goes to 0. The only term that survives is the third one, right? So when you pick J equals to 3, so for J equals 3, the above expression is just A3. Right? Does that make sense? Given by a rule, because otherwise, you put 3 here, 1, 3, 0, 2, 3 is 0, 3, 3 is 1, so only the third index survives. So you only get. That's what happens. Okay, this is, I'm only going to write this out once. I know it's painful to see this written out. So effectively what has happened is this has turned into AJ. We have AJ over here. Right? So that's not really very interesting, right? This is just, okay, I just changed the name of the index. That's all the effect of the delta symbol. Okay. Next, okay, I'll start the same thing. Right? This is what I've written down. And what I told you before, every time you see a repeated index, just combine with this paper. Okay. So my first question is immediately, without even bothering to ask about this, how many legs does this object have sticking out? Right? 0 legs, no legs, right? So what must it be?
Must be a scalar.
It's a scalar, right? So just from the, even before I've thought about what the object, just from the appearance of it, I can tell, okay, it's a scalar immediately. It's a scalar, it has no legs sticking out. Okay. We'll see, this scalar is so important, it has a specific name. I do the same thing I did above here. So what this delta does is gets rid of this summation, right? So right. Now if you explicitly write out this summation, it's A1 C1 plus A2 C2 plus A3 C3. What is this called?
Dot product.
So it's a dot product. So this is how we present dot product. Fairly simple and straightforward. And immediately we see the dot product has to be a scalar. Right? Nothing really fancy so far. But the point of these examples is just to make you comfortable with how you manipulate these diagrams. Okay. Yes.
I have a question. So if a leg is sticking out of a box,
Mhm.
it's a vector. If not, then it's a scalar. Can you distinguish between vectors and pseudo vectors through this?
So we'll see. We'll have to see particular examples, right? So should I leave this on, or should I? Is it okay if I erase this at this point, right? Actually, that's not making much sense because I'm going to leave this. But I'll go back. So, okay, what we've done is we've combined a vector with a delta. We've combined two vectors with the deltas, right? So the delta has been exhausted. Next, we move on to the Levi-Civita, right? So let's start with this. Right? And once again, I can just attach a vector. So what this symbolically is, so the index I has been summed over, so it doesn't really exist, right? And that is manifest in our diagram. The only two indices that really exist are the J and K indices, right? So those are the two what are called the free indices. So I can just say, okay, this object has really just has two indices. So I'll just call this object TJ. Just I'll rename it. That's fine. Now, okay, this object in itself is not really interesting, but the point I want to show with this is it has one really interesting property, which is what happens if I flip J and K? Right, that just comes from the rules I told you. So this thing is minus so this is our first example of a rank 2 antisymmetric tensor. By rank, I mean the number of indices the object carries. So a vector will be rank 1. This is rank 2, it carries 2 indices. Right? So this is our first example for an antisymmetric rank 2 tensor. Right? But again, that's all I want to say about this object. Nothing really more interesting about it. But, okay, we can move on. I'm going to go here. I'm going to leave this here. So we attached one vector to the Levi-Civita. How about we attach two of them? Right. Right. This is epsilon ijk. I can attach a vector. To see here, right? My first question is, what kind of object is this?
It's a rank one tensor, yeah, vector.
It's a vector, right? That should be clear because it only has one leg sticking out. Right. So previously we saw we combined two vectors to form a scalar. That was the dot product. Now we combine two vectors to form another vector. Now again, I'll just write it out in symbolic notation. Right? This is what I've written out. And the resulting object, it only has one index. The resulting object is a vector. That's fine. But this is a very special kind of vector. Right. Normally, we do what's called a parity transformation. And by a parity transformation, what we mean is we flip the sign of all the coordinates in the system. That's what a parity transformation is. Right? So if you have coordinates x, y, and z, they go to minus x, minus y, and minus z. Right? So what that means is if you have a vector A, it just goes to minus A. Right? If I apply this transformation. Does that make sense? So this vector is a special kind of vector. Normal vectors behave in a way when you apply this parity transformation, they go to negative of themselves. Right? But when I apply a parity transformation to this object, this becomes minus A. This becomes minus C. Right? So the minus signs cancel out. And the object is still plus. So an object that does not change sign under parity is called a pseudovector. Right? So this is our representation for pseudovector. And there's one more interesting thing. Again, this object is so common, it has a name. Can anybody tell me what the name of this object is? What we've done? What this operation is called? It's the cross product. Right? So what I've written is it's A cross sigma. Right? And why A cross C? Because I'm reading counterclockwise, right? So A cross C, that's how I'm supposed to read this. Again, with our description of the rules for how you should read it. Now it has another interesting property. I can flip A and C, right? So C comes over here and A comes over here, but I get a minus sign, right? I pick up an overall minus sign. But now C is here and A is over here. So now I read this as C cross A. Right? That's immediately apparent from the structure of the diagram. That if you interchange A and C, you pick up a minus sign.
And for this reason, we call it a pseudo tensor. Oh, sorry, a pseudo vector.
No, the reason it's a pseudo vector is because if you change the sign of all the vectors in this expression, the overall thing does not change. Right? Any other questions so far? Still nothing. We have not really done a lot of interesting stuff, but I just want to keep doing these manipulations so that we get used to it. Sorry. Okay, so we have almost exhausted the Levi-Civita. We have attached one vector to it. We have attached two vectors to it. How we just attach all of them? Okay, my first question, what kind of object is this? It's a scalar, right? It has to be scalar, no like sticking out. Fine. Okay, but how do we even read this object?
It's
Right, that's a question, right? Because previously, if this was a free index, you could just read C cross A, right? Okay, it's interesting. For a second, imagine there's a box over here. I'm just making this box P, right? So from the outside, what this looks like is A dotted with P, right? Just A dot P, right? But if you look really closely at P, what is P?
sort of like B cross C.
P is just B cross C, right? So right. But there was nothing really special about why I put the box over here. I could have put the box elsewhere. How about this box? Right? So if you put this box, then it looks like D is dotted with does everybody agree? If I look at the red box, it looks like B sitting outside. It's dotted with C cross it. Right? But again, there's one more option that we have, which is this one. Right? The point is these are all equivalent. Right? This one object carries all of these representations. Which might not be otherwise apparent if you just look at one particular representation.
So can we call it pseudo scalar?
This is a pseudoscalar. Right? Because scalars are not supposed to change a sign. Like think of a temperature field.
Yeah.
If you do a parity transformation, the temperature field should not change. But if you change the sign of everything, you pick up an overall minus sign. Minus A minus B, the minus sign cancels, but you're left over with the third sign. Right? So this is a pseudoscalar. Any questions? Okay, so we have looked at just basic ways of combining vectors and yes.
Can I ask a quick question?
Yes. There's a question from somebody in the audience, and then perhaps I can get to you.
Yeah, I had a quick question on the previous board where you wrote A, B, and K. So over there,
Yes.
am I allowed to switch A and K, let's say?
A and K, sorry, what is?
On the diagram, am I allowed to flip A and K? So K is the index,
Yes,
right?
you can. Yeah, you can flip A and K. Yes. So
And
if
so
you
what
flip
would
A and
that?
K,
Yeah.
if you flip A and K, right, as just if you flip A and K, you just get C, right? This is what you would get. You pick up a minus sign, but you can always read this as C cross A,
Right.
right?
Yeah.
Should
So
be
it
a
doesn't
question.
change anything. Yeah. Thank you.
ये जो हमारे पास ए डॉट बी क्रॉस सी है, क्या इसे हम जो है कर्नेकर डेल्टा के साथ लिख सकते हैं इंडेक्स की फॉर्म?
No, because in index notation, this is so this is just a Levy Vita contracted line. So no problem. Right? So okay. Still, I would say nothing really interesting. This is all pretty much basic stuff that you guys know. Now we can start talking about some interesting stuff. Start talking about some interesting arguments. Okay. I'll have to first give you sort of trust me on this, and then once we build this, then we'll see why this works and why it's important. Oftentimes, we come across an object like this. So the top bit is epsilon ijk. The bottom bit is epsilon lmk. And since the k's line up, right, they should be subnormal. Right? Now this object shows up quite a bit. Where it shows up, you'll see. But for now, we want to look at this object a bit more closely, right? First thing is, okay, this object has, how many indices does this have?
Four.
4 indices, okay, that's fine. Second thing is, what values can this object possibly take? So let's say this symbol can take +1, -1, or 0. This one can take +1, -1, 0, and be taking a product, right? So the product can also take values of +1, -1, or 0, right? That's what this object can be at most. Okay. Now, what I want to do is I want to try and come up with a decomposition for this object. And why might I be motivated to think that this might be, we can decompose it, right? So the epsilon can take on values +1, -1, 0. This object can take on values +1, -1, 0. We've seen another object which can take on +1 and 0, right? What object was that? The Kronecker delta, right? So if I put up a minus sign in front of a Kronecker delta, so it takes on values -1 and 0, right? But if I take a product of two Kronecker deltas, right, I can have with a minus sign up front, so that can take a value minus sign, but then I can have another term which does not have a minus sign in front of it. So I can vaguely start thinking maybe I can cook up some kind of a term using Kronecker deltas with the appropriate signs up front that might have the right kind of values that it can take, right? I can vaguely start thinking we'll try to make an effort for this, and we'll see, okay, how far we go. First thing I want to do is I'm just gonna rewrite all the indices up. So what we're trying to do is we're trying to come up with a decomposition for this object in terms of Kronecker deltas, right? So in what ways can I make Kronecker deltas out of these indices? Right? Well, one way is this. One way would be this, and one way would be this. Right? And I'll put up appropriate coefficients up front. Because I don't know what are the relative signs of the terms involved. Right? Now you might say, okay, why did I put only three? Well, these are the only three possibilities that you can come up with. Think about it for a second if you can try to make up another diagram out of Kronecker deltas from these symbols. Does anything come to mind? Right? So this exhausts the possibilities of how you can write these indices in terms of Kronecker deltas, right? So I will start by looking at this term over here. On the left hand, you see that if I flip I and j, right, I should pick up a minus sign, right? That's just the nature of this object. I'll look at these terms as well, but look at this term, for example. Right? By flipping I and j, what I'm doing is, okay, I'm taking this end, I'm attaching it to this end, I'm taking this end, attaching it to this end. It's the same thing, right? Same applies for the bottom index, right? But if I flip I and j over here, what I'm doing is I'm taking I, attaching it here, j attaching it there, right? This is what flipping the index really means. And likewise, this is what happens for this term. So notice this term is completely unchanged. These two terms basically morph into each other. So I have some hope thinking, okay, well, at least these terms change. This one is completely unchanged, right? So far, so good. Everybody following me, right? These terms change. This one is completely unchanged. The left-hand side tells me I have to pick up a minus sign, right? That's just a rule. So if this term is completely unchanged, it does not pick up a sign, it does not change into anything else. This term cannot be part of this, right? Because how am I going to pick up a minus sign if this does not change at all? Right? So that tells me immediately that C is equals to 0. Fair enough? Okay, so A and B. Again, if I flip I and J, these two terms morph into each other, right? And I have to pick up a minus sign. That's what the left-hand side is telling me. How can that be? Well, the only way that's possible is if these two terms have a relative sign. Right? They cannot be different by coefficient, unless or until the term itself picks up a minus sign, which it is not doing. It's just morphing into another term when I swap the indices, right? So if these two terms have a relative sign, then this goes into this goes into this, I can pull out an overall minus sign, right? But there's still this overall coefficient up front, which I don't know, right? Well, there's one way to figure it out. Just plug in some values of indices. So what I'll do is I'll plug in I equals to 1, j equals to 2, I equals 1, and equals to 2. Fair enough? So what I've done is on the left-hand side, I've written epsilon 1 to k, epsilon 1 to k. This is what I've written. Yes? The only non-zero term in this sum is epsilon 1 to 3, epsilon 1 to 3. Do we agree? So what is the value of this term? Plus 1, right? Left-hand side is +1. What's the right-hand side? What is this term? This is delta 1, 2, which has to be
0.
right? This is delta 1, 2. This is 0.
Left.
What about this one? Delta 1, 1.
1.
Delta 2, 2. Right? So on the left-hand side, I have 1 equals to A times 1. So A is just 1. Does that make sense? Any questions? Right? And I know this is rock solid because since this is an equality, right, it must hold for all values of A. So I can plug in a particular set of values, and if it holds for this, and I know it has to hold for those, so that allows me to figure it out. So what I've essentially accomplished is this. Okay. Nicely. If you see a diagram of this kind, immediately decompose it into this minus. I don't even need to write down the indices actually, as long as I'm consistent with where I put the external vectors or whatever I attach on the outside, right? And we'll see, and we'll now see an explicit example for this. So I'm going to leave this here, this rule over here, and we'll move to the first one. Okay. What is this?
Across product.
How would I read this? A cross B, right? So this is, but upon closer inspection, right, if I look, if P itself is also a cross product, right? So if I look in really closely, what P is, it's just right. This can happen. What I have on the left-hand side is this is a triple product, like a double cross product for this. Right, and I have the rule. We initially, so this is a very familiar diagram which we just saw, right? And I know how to break it down immediately. Mindlessly, I can write it down. As long as I'm careful when I place the vectors in the respective positions. So what is this? First of all, what is this term?
A dot C.
Times what?
B.
Minus so once I have that rule, I can just forget about, the deltas, indices, whatever. I can just plug in these things. And this is a very well-known vector identity. And I urge you to try to prove this by writing out vector components. And you'll see, why this solve is worthwhile, right? Even with index notation, you can get lost in the indices a bit. But all the work that we did was, okay, this is pretty neat, okay? But okay, still fine. Okay, you can say whatever. But here's one more example where we'll see the usefulness of this kind of representation. Is this clear to everyone?
Yes.
Any confusion? Right. So I'm going to move on to the second board, and hopefully this is our last example. And finally, we can have a physics example. So Angular momentum. Angular momentum is defined as L equals to R cross. We start off with this definition, right? Angular momentum is R cross P. R cross, what is P? P is MD. Yes, simple. Now, if you're in rotational motion, your tangential velocity is given by omega cross R. Yes, where omega is your angular frequency, right? R is your position vector again. Let me pull out the M from this is just a constant. But what do we have here? Right? We have a triple product again. Okay, I'm not done. I'll rewrite this over here. Let's put everything on the top. Okay, let's write out this triple product in our notation. So the way triple products work was this is R crossed with omega. So, yes, everybody agree? Is this a reasonable way to write this? Okay, so my first question is, what is this object? Is it a vector, a scalar, whatever?
Vector.
It's a vector. It has to be a vector, right? Because angular momentum is a vector. It has one free leg sticking up. Okay, now I'm going to take a bit of a leap of faith, which is, if you look at this thing, right? What is R? R is the position vector that points to the object, right? That tells you how far the object is relative to your axis of rotation, right? What is omega? It's used to an angular frequency, right? So the angular frequency, all the angular frequency tells you is how fast and in which direction your object is spinning, right? So omega in that sense is kind of arbitrary. It has nothing to do with the object itself, right? It only tells you whatever object that you have, how fast it's spinning and in what direction it's spinning, right? So let me not consider omega. Let me just detach omega from this because my point is it's not really fundamental to the object itself. Right? It just depends on how fast you spin the object, right? That's up to you. These position vectors, on the other hand, they point to the object itself, right? Where you place the object. So they're referencing the object directly. So once I detach omega, what am I left with? What is this object? What kind of it's a tensor, right? Okay. How many indices does this include?
So I mean, I can take a very wild guess over here. There is a metric tensor.
No, it's going to be even more interesting,
Okay.
right? So first of all, we see that like omega is sitting out here. I'm not throwing it away, but I'm just detaching it for now because
Right.
my grounds for detaching it. Okay, it's arbitrary, right? Because it doesn't really reference the object itself. So what really references to the object is this thing, right? The object in question, and it's a rank 2 tensor.
Moment of inertia.
Right? So based on our decomposition rule, that one, right? This is the kind of object that we have. I can immediately break it down. Let me put an R over here. R over here. And then I can put in the indices as I please. Yes? So what is this first term? It's R dot R, right? It's R squared. Times what? Delta ij
Yeah.
minus R. Don't forget we have an overall factor of M sitting outside, so This is your good old inertia tensor. Right? So now we can basically rewrite this. So this object, how many indices does this have? 2. Right? See, it has 2 indices over here. It's so special, it gets its own symbol. It's I sub ij. And remember, we have this omega sitting outside, right? Which we have detached. Since this is symmetric, right? I can attach the omega anywhere, doesn't really matter. So omega j summed over j obviously. And that's your angular momentum. So you see how it immediately just pops out from the diagrams. So I'm out of time. I had one more example if people are interested, if people want to stay, I can discuss, but I think for the sake of time, that's all I have to say. So any questions? Yes.
What would you say are the limitations of this representation?
The limits of this representation are that it can get start to get a bit clumsy if you have really long expressions. But again, that's a matter of taste, I will say. This is only one aspect which I've shown. I mean, this can be extended to vector calculus even. So we can calculate divergences.
This is where I was actually going to go, that in fields of mathematics like fluid dynamics, or when you're using fluid modeling to, model a few physical systems, so we get to deal with a lot of cumbersome vector identities.
Mhm.
Is it of any use in?
Yes,
let's say-
this can be economical. So if people are interested, I can do another follow-up lecture where I do the vector aspect of it, like the calculus aspect of it. I can do a derivation of the Maxwell stress tensor in electromagnetism, right?
Or maybe something like a Navier substitution.
Okay, I'll look into it. Yeah, maybe I can try that as well. Yes.
I have a question regarding the vectors itself. So when we were doing a dot product, we generally define a dot product between a vector and a one form. The one form itself, so in this notation, we won't really distinguish between a vector and a one form.
Right. I mean, well, I'm not that well versed in that language, but I mean, when you define a dot product, right, it's defined with a Kronecker delta, which is your metric for free space, right? So that metric takes you from 2 vectors and that takes you to a one form, right? So it's kind of encoded somewhere in there, but we're not explicitly making a difference between a one form, which is like a row vector versus a column vector.
So like if you don't have the Kronecker delta as a metric, for example, that's two vectors.
That I haven't looked into. So if you want to extend this to 4 vectors, right? Then you will have your eta mu, your flat Minkowski metric. I can try to look into it. That'd be interesting. But even for general identities, because for a lot of time, especially in electrodynamics and fluid dynamics, you're dealing with 3 vectors. So that's likely to scope. But I'm pretty sure people might have extended it to 4 vectors. Any other questions? Yes.
Are we determining these notations are generally mathematically coherent?
Mathematically coherent. I suppose the only answer I can give in that case is that the point of the diagram is to encode the symbol, right? So as long as the diagram has all the properties of the symbol, right, there's an equivalence between the two. So it should be fine, I suppose. So for example, with the Levi-Civita, the way I constructed the symbol is, I didn't tell you that epsilon 1, 2, 3 is +1 or epsilon 1, 1, 2 or whatever. If 2 indices are repeated, it has to be 0. That followed as a consequence of the properties that we endowed it with, right? And the symbol just has to obey those properties. That's it.
We cannot encode all properties at once, right? That will be kind of another work. So what can we do to ensure that what symbols the what properties the symbols have been given, they would follow all the other properties of grid disease, vector space, subspaces,
So as far as this notation is concerned, this is only for computation in the sense of manipulating symbols, right? So all you're doing is think of it like just using a different language to write down the same expression. So I don't have to use English alphabets to write down my symbols and manipulate them algebraically, right? I could use Arabic alphabets as long as I'm clear in my head that the manipulations are logically consistent. So the diagrams is essentially, think of it like another language, right? So it's basically the same information. The point of the diagrams is the diagrams are a bit more visual, right? They're easy to see. You can move things around, shake things up, and that might help you in manipulating them. But there's no new information or there's no information lost essentially when you switch to this point of view. It can be cumbersome in some aspects, but you can say the same for the other approach. It has its limitations in the sense that you cannot do explicit numerical computation with it, right? In the end, if you want to do explicit numerical computations, you have to plug in numbers, right? But as far as manipulating an algebraic expression is concerned, it's exactly equivalent. Right. So with that, I will wait. Thank you very much.
Thank you.